A consequence of the second law of thermodynamics is Carnot's theorem with two main statements. According to the first one, the thermal efficiency of the reversible Carnot cycle is independent of the material properties of the thermodynamic system performing the cycle. We already saw that the efficiency eta defined by the ratio of the work W' done in the cycle to the heat Q1 absorbed in the cycle is equal to the difference between the heat Q1 and the heat Q2' divided by Q1, where Q2' denotes the heat released in the cycle. This ratio was also expressed as the difference between the temperatures T1 and T2 of the hot and cold heat bath used in the cycle over T1. The first consequence simply tells us that this result holds for an arbitrary working substance performing the cycle. In order to prove the first statement of Carnot's theorem, let us consider two irreversible Carnot engines C and C' connected to two heat reservoirs at the temperatures T1 and T2, where the temperature T1 is greater than the temperature T2. We suppose that an ideal gas is applied as working substance in the Carnot engine C, whereas the Carnot engine C' uses some other working substance. Let us assume that the thermal efficiency eta of the Carnot engine is greater than the thermal efficiency eta bar of the Carnot engine C'. First, the engine C starts its operation by extracting the heat Q1 from the hot reservoir at the temperature T1, does the work W' given by eta times Q1, and rejects the heat 1 minus eta times Q1 into the cold reservoir at the temperature T2. Then the engine C' starts its operation in the reverse direction with the amount of working substance allowing the engine to dissipate the heat Q1 into the hot reservoir, compensating the amount of heat extracted by the engine C in the first step. The work W' done by the engine C' during its operation is equal to minus eta bar times Q1, and its magnitude is less than the work eta times Q1 done by the engine C as shown in the work balance equation between the two engines. At the same time, the heat 1 minus eta bar times Q1 is extracted from the cold reservoir by the engine C', and the heat balance equation states that the extracted heat is greater than the heat 1 minus eta times Q1 rejected into the cold reservoir by the engine C. This relation shows that the whole process cools the cold reservoir. By combining the operations of the two engines, the net work done by them is equal to the difference between eta times Q1 and eta bar times Q1. This expression is positive and the system has done useful work at the expense of cooling the cold reservoir, which is impossible since it violates the second law of thermodynamics. As a result, the assumption that the thermal efficiency eta bar is less than the thermal efficiency eta cannot hold. By reversing the direction of the operation of the whole system, we can prove that the inequality stating that eta bar is greater than eta cannot hold either. Then we conclude that the thermal efficiencies eta and eta bar must be equal, that is, the thermal efficiency of a Carnot engine does not depend on what kind of working substance is used by the engine. The second statement of Carnot's theorem is the following. If a Carnot cycle or any of its infinitesimally small stage is irreversible, then its thermal efficiency is smaller than the ratio of T1 minus T2 to T1, where the hot and cold reservoirs used in the cycle have the temperatures T1 and T2. This consequence can be demonstrated with the concrete example. Let us consider the steps of the isothermal expansion and compression in a Carnot cycle indicated by the curves between the points A and B, and the points C and D on the isotherms at the temperatures T1 and T2 in the pressure volume diagram of the cycle. We suppose that the Carnot cycle is irreversible because the moving piston of the Carnot engine applying an ideal gas as a working substance has friction with the wall of the cylinder filled with the gas. Since the heat produced by the friction is absorbed at least in part by the heat reservoirs of the engine, the heat Q*1 transferred from the heat bath at the temperature T1 is less than the heat Q1 transferred from the same heat bath in the case of the piston performing a frictionless motion in a reversible process. At the same time, the heat Q'2 rejected to the heat reservoir at the temperature T2 is greater than the heat Q'2 rejected to the same heat reservoir for the piston moving without friction. As a result, the ratio of Q'2 to Q*1 is greater than the ratio of Q'2 to Q1. In the case of the irreversible Carnot cycle, the thermal efficiency eta bar of the cycle is equal to the difference between Q*1 and Q'2 divided by Q*1, or 1 minus the ratio of Q'2 to Q*1. Similarly, the thermal efficiency eta of the reversible Carnot cycle is given by the difference between Q1 and Q'2 divided by Q1, or 1 minus the ratio of Q'2 to Q1. By virtue of the inequality obtained for the ratios in the expressions of the eta bar and eta, the thermal efficiency eta bar of the irreversible process is less than the thermal efficiency eta of the reversible process. Since the expression obtained for eta is equal to 1 minus the ratio of the temperature T2 to the temperature T1, we can write that eta bar is less than 1 minus the ratio of T2 to T1, or the difference between the T1 and T2 divided by T1. Then we demonstrated that the thermal efficiency of an irreversible Carnot engine is always less than the difference between T1 and T2 over T1. We saw that the first part of Carnot's theorem states that the thermal efficiency of a reversible Carnot cycle is independent of the material properties of the working substance performing the cycle. The mathematical formulation of the theorem shows that the efficiency depends on only the operating temperatures of the heat reservoirs of the Carnot engine. Based on this fact, we can fix the scale of the thermodynamic temperature already introduced in the discussion on temperature. In order to do that, let us consider the operation of a system that consists of 3 reversible Carnot engines and 3 heat reservoirs at the temperatures T1, T2 and T3. Let us suppose that the first Carnot engine in the system absorbs the heat Q1 from the heat bath at the temperature T1, does the work W1' and rejects the heat Q2' to the heat bath at the temperature T2. Similarly, the second Carnot engine extracts the heat Q2 from the heat bath at the temperature T2, delivers the work W2' and dissipates the heat Q3' to the heat bath at the temperature T3. Here we assume that the same amount of heat is rejected to and absorbed from the heat reservoir at the temperature T2, that is the heat Q2 is equal to the heat Q2'. Finally, we also suppose that the third Carnot engine absorbs the heat Q1, that is the same heat from the heat reservoir at temperature T1 as the first reversible heat engine does the work W3', and rejects the heat Q3', that is the same amount of heat to the heat reservoir at the temperature T3 as the third reversible heat engine does. Now we determine the thermal efficiency for each reversible engine during its operation. The thermal efficiency eta1 of the first Carnot engine is defined by the ratio of the work W1' done by the engine to the heat Q1 absorbed in the Carnot cycle. We already saw that the work W2' can be written as the difference between the heat Q1 absorbed by the engine and the heat Q2' rejected by it due to the first law of thermodynamics. Then the efficiency is simply equal to 1 minus the ratio of Q2' to Q1. Similarly, the thermal efficiency eta2 of the second reversible engine defined by the ratio of the work W2' delivered by the engine to the heat Q2 absorbed by it, is equal to 1 minus the ratio of the heat Q3' rejected by it to the heat Q2. Since we assume that Q2 is equal to Q2', we can write the efficiency as 1 over Q3' divided by Q2'. Finally, the thermal efficiency eta3 of the third Carnot engine defined by the ratio of the work W3' done by the engine to the heat Q1 absorbed by it, is equal to 1 minus the ratio of the heat Q3' rejected by the engine to the heat Q1. Since the thermal efficiency of a reversible Carnot engine does not depend on the material properties of its working substance, as stated in Carnot's theorem, the efficiency has the same value for given temperatures of the heat reservoirs used by the engine. As a result, the ratio of the magnitudes of the heat absorbed and rejected in the Carnot cycle depends only on these temperatures. We already derived the explicit dependence of the efficiency on the temperature for a Carnot engine using an ideal gas as a working substance, and Carnot's theorem states that this explicit form is valid for any other type of working substance. However, we keep the dependence of the efficiency on the temperature in a general form and we only conclude that the ratio of Q2' to Q1 is some function f of the temperatures T1 and T2 of the heat reservoirs exchanging heat with the first engine. Similarly, the ratio of Q3' to Q2' can be written as the function f depending on the temperatures T2 and T3, and the ratio of Q3' to Q1' can be written as the function f depending on the temperatures T1 and T3. Now we can multiply and divide the ratio of Q3' to Q1 by Q2', and write it as Q3' over Q2' times Q2' over Q1. If we substitute the functional dependencies of these fractions on the temperature into this equation, we can state that the function f depending on T1 and T3 is equal to the function f depending on T2 and T3, times the function f depending on T1 and T2. The left-hand side of the equation does not depend on the temperature T2, whereas its right-hand side does. Then we conclude that the function f depending on T1 and T2 has the form given by the ratio of another function g depending on T1 to the function g depending on T2. Similarly, the function f depending on T2 and T3 can be written as the ratio of the function g depending on T2 to the function g depending on T3. If we substitute these forms into the right-hand side of the last equation, we can write the function f depending on T1 and T3 as the ratio of the function g depending on T1 to the function g depending on T3. Generally, we can write that the ratio of the heat Q' I rejected to any of the heat reservoir in the system to the heat Qj absorbed from another one is equal to the ratio of the function g depending on the temperature Ti to the function g depending on the temperature Tj, where the indices I and j can be 1, 2 and 3. Here the function g is some monotonic function of temperature satisfying these relations, but it is not determined yet. When Lord Kelvin defined the scale of thermodynamic temperature, he simply selected the identity function for g, and established the relation stating that the ratio of the absorbed heat to the rejected heat is equal to the ratio of the temperature of the cold reservoir to the temperature of the hot reservoir. As a result, the thermal efficiency eta1 of the first reversible heat engine is equal to 1 minus the ratio of the temperature T2 to the temperature T1. We have similar expressions for the thermal efficiencies of the other two engines as well. We already mentioned that this equation is derived for a Carnot engine using an ideal gas as a working substance, and later it was generalized in Carnot's theorem. Therefore, the choice made by Kelvin gives the correct form for the temperature dependency of the efficiency. This equation can be used to express the temperature T2 of one of the heat bath as the temperature T1 of the other one, times 1 minus the thermal efficiency eta of the reversible Carnot cycle. We can establish the thermodynamic temperature by fixing the temperature T1 as a reference temperature, and measure the thermal efficiency eta of the Carnot cycle. In practice, we choose the triple point of water as the reference temperature T1, which is equal to 273.16 Kelvin. Since the heat absorbed in the Carnot cycle is equal to the work done in the first step of the cycle, that is the isothermal expansion of the gas, the thermal efficiency is just equal to the total work done in the cycle divided by the work done in the first step. By measuring it in the reversible Carnot cycle, we can determine the thermodynamic temperature T2 for the reference temperature T1 of the triple point of the water. We note that because the reversible Carnot cycle is just an idealized approximation, we cannot obtain accurate values for the thermodynamic temperature by applying this method. However, the Clausius-Clapeyron equations can be derived from the equation defining the thermodynamic scale of temperature, and the comparison of their graphs with measurements can provide accurate values for the thermodynamic temperature.